From MBN Nanomaterialia from Italy. And then we will continue with Patricia from Sintef before having coffee break at 3:30. So the floor is yours.
Thank you.
Thank you.
Thank you. So the talk today is about thermoelectric material processing, which is quite vague as a talk because the thermoelectric materials are so different. So I took the liberty to just give an overview of the techniques that we have been exposed to, let's say, and the materials. So material processing is something more than just creating the material. There are a lot of steps that I'm not going to talk about because beside the actual production of the thermoelectric material, there is also dicing, coating, assembling, and these are all steps that will be part of next talk. And this is indeed a simplification of the different steps that are needed to arrive to a thermoelectric generator or device, because they are much more if you really look into the details. And each of them has a quite specific process, sometimes, many times, a different company that you two have to deal with. So the story can be really long, really quickly if you want to give all the details. So what I want to do is just focus on raw materials approaches and thermoelectric material synthesis. So you have seen today already thermoelectric materials can be quite diverse in terms of elements that are involved, in terms of combination of crystal phases and systems, all delivering the unique ZT and optimized for a specific temperature. From my point of view of a company who is producing material, all this is very interesting, but we focus more on the actual material production route. And if we are lucky, we end up with something that has a very specific phase diagram in which you can not much make mistakes. If you do the melting from this combination of percentages of elements, you end up with the correct phase. And in this case, it's easy. Of course, you want to maybe dope it with other elements, but let's say it's facilitated the approach from a melting point. Because at the end, you have always to start from the elements, trying to put them together and to form the specific phases that are required to deliver the thermoelectric properties. Other cases can be more tricky, such silicon germanium. In this case, also, it's quite simple, the phase diagram, but you really need to get across this liquidus temperature quite quickly in order to get the percentages of elements that you really want. This, of course, can be done, and Thermagy is doing that quite neatly with a process that they will describe later on, in which the melt is cooled quickly using a moving and a usable substrate. The materials are put together, melted, and then crystallized into wafers. And this allows to go across quickly this zone and avoid the segregation and separate formation of other phases. And we are still talking about basically two elements with their dopants. If you are talking with more elements, things are even more complicated. If you're lucky, you can get it quite quickly, but the amount of different phases that can be formed using the approach of melting everything down and cooling is basically exponentially increasing. especially if you want to add other dopants and substitutional elements to increase the properties of the thermoelectric material. In this case, yeah, this is a ternary diagram for titanium nickel tin, but titanium is oftenly substituted with zirconium, hafnium, and the tin itself can be substituted by other elements, each of them driving the cooling pathway to a different route. Another case that we have heard today about is the tetrahedrite. The crystal structure here is quite complex, but there is a quite specific thing about tetrahedrites is that we can obtain them naturally. It's occurring naturally, and we can hypothetically use it directly to make our thermoelectric device. So this is an example of from a museum. Not always it is in this form, and it is not always containing the right element to have a proper thermoelectric material. But what one can think about having this material already available is to grind it down, use ball milling to make it a very fine powder, compact it into a pellet that you can even test. And what you end up with is almost a thermoelectric material, because it's a tetrahedrite, but the thermoelectric properties are not yet there. So I'm simplifying, but this is more or less the concept also in start. We needed to change a bit what nature provided us, and we try to add dopants and to the ball milling part in order to compensate for this lack of properties, adding substitutional elements to copper and compensating with more sulfur, more antimony. And the results are quite good in general. So from a perspective of material production, of course. Copper is still there, antimony is still there, sulfur is still there, all well mixed. So the ball milling approach, even adding the separate element, worked. We have iron, we put it iron, but we also can see spot here and there of iron because iron was present in the original mineral, actually in the form of pyrite in some cases. Same story for arsenic, which is there from the ore itself. And then, of course, there is oxygen and silicon. This, again, is from the ore. We cannot completely get rid of the quartz that is in the system. But since we arrived here, we can think about, okay, which is the good ratio between mineral and synthetic material that get us the good performances? How we can get rid of the silicon oxide and the quartz? So this was one of the fundamental questions of start, and we tested this approach by ball milling and also by melting, starting directly from the elements to form the tetrahedrite, so a completely synthetic tetrahedrite. Similarly for the melting approach. The melting approach was not super effective. We realized quite quickly that these elements have so quite different melting points. They are reacting in different ways to form those segregation that we expected to some extent, but we don't want to have. And we tried further pre-mixing these by ball milling in order to have quite homogeneous composites. But again, segregation were occurring, so this was not a pathway forward. The ball milling also had his problem, but eventually we solved them. There was formation of alternative phases like fematinite, but adjusting the amount of dopants and the milling condition, we arrived eventually to form the synthetic tetrahedrite that we wanted. So let me digress a bit more on ball milling. What is it exactly? So in the ball milling, this mixing is happening at solid state. We are putting together at different phases all the material that we started with. There are effect of flattening, welding, cold welding, and all of this, after a certain amount of time, brings you to the formation of new phases, the dispersion of oxides or hard phases that you have in the material, and eventually the formation of what you might expect to get from the ball milling, which is the final phase. There are different types, of course, of ball milling, from a triton mill to planetary mill, vibratory mill. These that you can see also from the pictures are at lab scale mills. It's not trivial to upscale the ball milling, keeping also the high energy that sometimes is required to put together metals. If you have to put together brittle materials, oxides, ceramics, it's a different thing, but with metal you really need to go to higher energy and control also the contamination that you might get from the milling materials. Oops. So vibratory mills are moving more or less this way, and planetary mills are revolving and rotating. They have limits on how much you can get energy from that. A triton mill are just moving a certain axe, putting everything in rotation, but these are very good for attrition, not really for alloying. As I was saying, if you start with the ductile particles, you tend to flatten them. You flat and you fold, and you eventually get something that is thoroughly mixed. Intermetallics and brittle particles tends to form really nanometer size or inclusion into the final material. And this is more or less the evolution that you normally expect from this material. This below is actually something that we took as a sequence of images at different milling times. So you see, you start with some cluster after some time of milling, and you end up with a complete dispersion, almost complete. Sometimes you always need some thermal treatment to fully alloy it. So, but one thing is alloying, one thing is forming specific crystal structures. In some cases, when the thermodynamics is in your favor, you can obtain some mechanochemical reaction, formation of completely new phases, or removal of oxygen from iron to get aluminum oxide, or in this case is formation of titanium carbide in a matrix of aluminum. And these are all nice effects, and the ball milling was originally thought as a way not for this kind of purposes, or more for improving the mechanical properties of the material. And the idea is that you want to avoid dislocation movement on your crystal, and a way to achieve that is to increase the amount of grain boundaries and have them with a very small size, and possibly also to have some nano oxide dispersed in the matrix in order to block for the possible reaggregation or movement of these parts. So I know this is not directly connected with thermoelectric materials, but we will get to that. So these properties are used, at least in our company, to deliver different effects. Put together immiscible materials, have nanodispersoids, obtain CERMET, so dispersion of carbides in the metal matrix, obtain compositionally complex alloys. But these properties are also relevant to the thermoelectric materials. because the amount of grain boundaries that you can deliver and keep into a thermoelectric material also helps in the decoupling of thermal conductivities and electrical conductivity. So I don't want to go into the detail of this because I think you already heard a lot today about what is thermoelectric materials. I'm not the best person to go into these details, but the key point is, yes, that the effect of ball milling on the material helps also in this direction. So sometimes, even if you have a material obtained by casting, it's worth to do crushing and ball milling in order to get this nanostructuring effect that helps in the overall final properties. And here I have some examples of what happened during a ball milling in some different cases. This is a half Heusler, P-type, cobalt-based, and you can see it's quite confused, but it's the peaks are more or less in the same place. Probably it's small for you to see here, but these are XRD spectrum taken at different milling times. And if it is a short milling, a medium or long milling, they all ends up in the same place. This means that the formation of the Heusler is always happening. So it's an easy system, this for ball milling. The dots are basically where we should see the elements appearing. We start from the elements, for example, tin here in orange, and it disappears basically immediately and informing the Heusler phase with this composition. If we change composition, the story is different. Well, this is not fully appearing, but here you see there is an evolution in time of the peaks of the different elements into the final formation of the Heusler. Here we need to perform the ball milling for a certain time in order to have the final phase. Luckily, it is the phase that we need without many or substantial amount of other intermetallics, but yet it's a completely different behavior triggered by the initial composition of the that we are asked for. Yet a different example is this one. It's magnesium antimonide. Here we, beside the problem that was mentioned also this morning about the magnesium leaving the system and basically depleting the material from one of its components, we have seen also the problem of putting together actually bismuth and antimony. So that we had to force the formation of a magnesium bismuthide, and we added just antimony to that. And after some milling trials, you see that bismuth is appearing as a peak because antimony is taking completely its place, even if the amount were balanced in order to get the final required alloy balance. And eventually this was solved partially by increasing magnesium and also by adjusting the antimony and bismuth phase. But this introduces another concept, which is the approach in multiple steps, using a master, obtaining a master by ball milling, and then acting on that as a precursor for forming new materials, which is an approach that we also used in with the Tetrahedrites. We tested actually 3 approaches. One is, okay, we get the natural occurring tetrahedrite. We want to substitute X%, in this case 20%, with synthetic one, and we just add the synthetic one, regardless of all the contaminants. Or we just do an addition of these elements. So in this case, we've preformed the tetrahedrite and we add in the second step. In this case, we just add the elements and we do the ball milling directly with the tetrahedrite. Or we can do it more in a more complicated way. Look at the actual composition of the mineral, compensate with the missing elements. So if, for example, we have already 3-4% of iron, this limits the amount of mineral that we get, because the amount of iron coming from the mineral is already completing the overall amount that we need, and we just add the missing elements that needs to reach the target. We tested all of these, and looking into the overall processing, the performances, etc., we ended up using this approach for the final material production, which means that we have more than one step of ball milling. We have a formation of a master batch, which is the synthetic tetrahedrite. We can, of course, have a check of the properties, and if it is okay, we can proceed with the second step of ball milling, in which the mineral is introduced and mixed with the synthetic tetrahedrite. Then, of course, we have sieving, and we have possibly another ball milling step for the coarse fraction, in order to get more efficient in the overall powder production route. You can see here different equipment for sieving, for the ball milling itself, and for the filling of the milling chambers. Good. And we still have just powder at this point. We are not yet arrived to consolidate, and we have seen already all of these possible routes that can get us to this point. After having realized the powder, we can consider further steps. These are also considered for standard bismuth telluride production, homogenization steps with annealing on the powder to completely form the final phase, if it is not yet formed during the ball milling, or some control over the morphology if it is needed for the downstream consolidation processes, which could be many. So this list is not fully related to thermoelectrics. This downstream production routes that we see as a company producing materials for the powder metallurgy sector. So there are additive manufacturing techniques, thermal spray techniques, direct energy deposition. What we are using in start are SPS, spark plasma sintering, and we will have shortly a test also by hot isostatic press, which is probably you know already quite simple in concept method for consolidating powders. You need in some cases a capsule. For the hot isostatic pressing, it has to be metal. For the cold isostatic presses, also in rubber. And you increase the pressure in the hot case with argon. You can go up to 2000 degrees. In the cold isostatic press is room temperature filled with water. That's why you need a rubber. And we can go up to 3000 atmospheres. This is a picture of the equipment we are using. But of course, if you first do the cold isostatic press, you already have a sort of consolidated pellet that you can put into the hot isostatic press to have a sort of thermal treatment in pressure without the need of the capsule. The capsule is needed because if argon gets into the open porosity, basically is not affecting at all the compaction effect of the material. It's just keeping those porosities open. You need to have it closed. The SPS instead is something developed in Japan as a way to consolidate in a fast way powders. What you are seeing here is not exactly fast SPS. It's a machine that we have, which is a current-assisted hot press. It is similar in principle, but the pulses and the amount of energy and the shape of the curve that is of current that is passing through the material is completely different in this case. Here we are talking about bursts of electrical energy passing through the powder. The powder is put in a let's go to the next one directly, onto a graphite mold. So current is passing through it, and going through the powder and with the action also of the pressure on top of it, it's a way to reach in minutes almost full consolidation. And this gives us the possibility to get these pellets in different forms. This is one coming from our machines. I keep this because, as you can see, it's not neat as a shape. These materials are quite brittle, so this is another aspect which is quite tricky about handling these materials and having them consolidated. You end up with something that is very prone to breaking back into pieces, but what you actually want is some nice pellet that you can dice and possibly coat and metallize and integrate in a system. So we just covered a bit of this part to almost get to talk about the pellets with the metallic coating, but there is still a lot. And every material has its own route throughout this production of thermoelectric devices. And it's finished. I didn't check the time, so I don't know if I've been quick or
Yes.
long. I've been quick.
Yeah. Other question?
Because this could be a problem in terms of industry, in terms of process for industry.
Yeah.
How much do you think you lose?
This is a question for the next talk.
Okay.
But yeah, it's the losing of material throughout the different steps. You can imagine it contributing a lot to the inefficiencies of the material production. So in some cases, to get rid of this problem of material lost during cutting, you try to get this is not anymore the okay. You're trying to get from the SPS shapes that are already aligned with what you want to integrate eventually. But in some cases, this is not possible, so you have to do wire cutting in some cases, or even water jet cutting are seen used for in some cases to get the final shape. And the material loss is depending on the techniques that you are using. There are material losses also in the different steps of the production. In the powder metallurgy route, surely we have some few percentages of each step due to handling, basically, of the powders. And since we are working with a pilot scale in the range of kilograms, we are considerably in a good shape. A few percentages is not much. But if you are working at a lab scale, yeah, it's even worse, the ratio between what you have lost and what you are keeping. That's why we are trying to reuse the coarse powder after receiving. This is possible with systems that are not much prone to oxidation like the Tetrahedrite. It's more difficult with materials like magnesium antimonide or magnesium silicides, because in those cases you are trying to keep the whole process in inert atmosphere. So instead of recycling them, probably it's better to try to get directly the particle size distribution that is effective for consolidation.
And another thing, in the last slide you showed that the small pairs had already some contacts.
Yeah.
What are the contacts and how do you prepare them?
Also, that one is for the next talk. Yeah. Well, not exactly the next talk, but the after one, okay. The one from IGS. So. you keep notes of the question.
Yeah, thank you very much. Any other questions? Yes. Questions? From Slovakia.
Yes, thank you very much. Maybe you know we are working in high energy ball milling field. All our carriers, basically my father, like about I don't know, for more than 40 years, and me maybe 14 years now. So it's very nice to see that you really have shown this technology as very good also for this community. So that's very nice. So I would like to ask, you have shown these laboratory scale devices that we are using in our work, but in your work you are using, like, let's say, conventional ball mill for your processes?
No, we are designing and manufacturing our own ball mill machines. This allows us to go from the lab scale to the industrial scale quite, it's not easy, but we will have at least an idea how to move from one step to the other. Yeah, they work more or less on the same principle, which is vibratory mill, aligned to that of the specs, more or less.
Okay. And you mentioned that you were playing around with the ratio between the synthetic tetrahedrite and the mineral from nature. So what was the ratio that is like the best? What do you
I
have
think
this?
the last figures are about 35% of mineral into synthetic tetrahedrite.
Okay. Okay, thank you.
That works the best from the point of view of the thermoelectric figures.
Okay.
And only with one kind of mineral, yeah. Not all the minerals are equal. We put the label tetrahedrite, but each mine has its own composition. So in some cases you have a lot of pyrite that is absolutely not working for the thermoelectric properties. In other case you have a lot of siderite, I've seen, yeah. But in some places you get the good mineral.
From Alvisa was very interesting. You're receiving a lot of questions also from online.
I don't
Or maybe I
understand.
was not explaining myself.
No, maybe curiosity. But I don't understand if Ines wants to pose a question, because I see her on the screen. But Ines, do you have a question? Can you switch on your phone in case? No. So,
Okay.
sorry, false positive. You were good.
So you are safe. Okay, then, so with that, we will thank you again, Alvise, for your talk.
Thank you.